Hello, this is Jishan Child from JC Tuition, and today we're going to talk about electron arrangement and atomic orbitals. So you might remember the typical structure for an electron, where we have the nucleus, and then you have shells around it, and you might be familiar with that from GCSE. Now, and each shell has a different amount of energy, and they can hold a different number of electrons. So you might be familiar with this from GCSE. The first shell can hold 2 electrons, the second shell can hold a maximum of 8 electrons, and the next shell can hold a maximum of 18 electrons. If you want to work out how many numbers of electrons a shell can hold, you just use 2n squared, where n is the shell number, and you can work out the maximum number of electrons each shell can hold. So we've established that each shell has a different energy level. So let's say 1, 2, 3. But each of these also have what we call sub levels of energy. So 1 has an S sublevel, 2 has S, but it also has what we call P. This all makes sense in a minute, I hope. And 3 has S, P. He also has a D sublevel. So 1, 2, 3 is our main energy levels. These are our sublevels. There's also F. It goes on, and they all have slightly different energies, and it's increasing energy as we go up this way. 20 is a more complex description of electrons in atoms was described, and you might hear this. It's called quantum mechanics, and this equation here, which you don't need to know for this video, is Schrodinger's equation. It basically describes an atom mathematically with an equation, and the solution to the equation actually gives us the probability of finding an electron within a given volume. So electrons are no longer considered just part of a particle in a shell surrounding a nucleus. It's more like there's a negative cloud of energy, electrons, around the nucleus, and the probability of finding an electron you can work out through a wave function. So, and the solution to the equation gives us the probability of finding an electron within a given volume, and that space is called an atomic orbital. No longer considered to be a particle, but a cloud of negative charge surrounding a nucleus. And the electrons fill a volume of space, and these are known as atomic orbitals. And this diagram shows you atomic orbitals. So this is our, I was talking about the sublevels. So these are s orbitals. They're a spherical shape. There's p orbitals, which are like a dumbbell sort of shape. There's also d orbitals, f orbitals, and their geometries clearly get a bit more complex. Most A-level specifications only need you to know about the shapes of the s and p orbital. And these shapes, like I said, represent a volume of space. And it basically tells us there's a 95% probability of finding the electron here. The electrons are a cloud. They're not in just one static space. The quantum mechanics has taught us that. So we can, if we know the orbitals in which the electron's in, we know it with a 95% certainty that it's in that space. So let's draw our energy level diagram again. So we've got increasing energy, which I'll denote by E. So we've got our first energy level, we've got our second, and we've got our third. And they have their subshells, which are sort of their sub-levels, which are the s orbitals. We said the second has s and p orbitals. 3 has the s, p, and d suborbitals. Now what's important to note is that a single atomic orbital can hold a maximum of 2 electrons, okay? So just 2. So an s orbital can hold up to 2 electrons, so I've just denoted that as 1s. 2, same thing, it has a single s orbital in the second energy level, but it also has 3 p orbitals, so we say that's 2p, 2p, and 2p, each holding also 2 electrons each. So p orbitals can hold a maximum of 6 electrons in the p sublevel. And again, the third energy level also has the 3s orbital. It's 3 p's, 3 lots of p orbitals. Like we said, can hold 2, 4, 6, 3 electrons each. And there's also d orbitals, and they come in groups of 5. So we've got 3d, 3d. So they come in groups of 5, and they can hold 2 electrons each. So a total of 10 electrons can be held in the d sublevel. The energy level diagram showing the subshells, and each box basically represents an orbital which can hold the electrons. So the first main energy level is the s orbital, and then the second main energy level we have the s and p orbitals, and the p orbitals, they each have equal energy. Okay, and then the third energy level has our SP and D sublevels. Again, D higher energy than P when compared to the other D orbitals. So you need to notice here, so we were going in sort of ascending order of the first energy level and then 2, 2p, 3s, 3p, but you notice 4s just comes with just before 3d. That's because 4s actually has a lower energy than 3d. So hence it comes preceding 3d. And another thing I just want to talk about, and we don't want to go into too much detail because I don't want to touch into the realm of quantum mechanics, but electrons also have a property called spin, where two electrons in the same orbital must have what we call opposite spin. And we show this by, so remember, each orbital can hold a maximum of 2 electrons. So we show they have opposite spins by doing one up and one down. That's the 2 configurations electrons can take. The periodic table now, I feel like this demonstrates what we've been talking about quite nicely. So hydrogen has 1 electron, so we just say it's spin down in the s orbital, and then as the number of electrons increases, we go across the periodic table. You can see the 1s orbital is completely full. We go down to lithium. So the rule is we fill in the electrons with the lower energy first, okay? And then when we get to the atomic orbitals of the same energy, so for instance the p orbitals, each atomic orbitals fill singly. So as you can see, there's 1p, and then for carbon we have two electrons in each orbital, then 3. So you do it singly, and before they start pairing up, as you can see as we go along, as the electrons increase. And yeah, no atomic orbital can hold more than 2 electrons. So again, to recap, the atomic orbitals of lower energy are filled first. Atomic orbitals of the same energy fill singly before the pairing starts, and that's simply because electrons repel each other, and no atomic orbital can hold more than 2 electrons. To write it in a shorthand way rather than drawing out all the boxes. So let's have a go at that. So let's do sodium. So you might recall that sodium has 11 electrons. So let's try that. So remember, we start off with our first main energy level and we have an s orbital there, yeah? And each one s orbital can hold 2 electrons, so we do a superscript and write 2. All right, that's fine. Then we go into our second shell, or second energy level, which has our s orbitals, and it also has p orbitals. The s orbitals can hold 2 electrons. Remember the p subshells, sorry. There's 3 orbitals of equal energy holding 2 each, so we can hold a maximum of 6 electrons. So we've done 2, 4, add 6, that's 10. And then we have to move to our third energy level for that last electron, the 11th electron, which first we do the energy of the lower orbital energy, which is just the s orbital, and that can hold the 1 electron. So we've got 2 electrons, then 8, then 1. So you can imagine that in the shell diagram. So 2 electrons in the first shell, then 8 electrons in the next shell, and then 1 on the last one. Okay, let's try another example. Let's try calcium, which has 20 electrons, by the way. So again, we do the s orbitals first, the first energy level, and we move up to the next energy level, which is the second energy level, and the s orbital can hold 2 electrons and the p orbital can hold 6. Then we move on to our third energy level. The s orbital again is lower energy, which holds 2. Then we have the p orbital, which can hold 6. And now you might be tempted to go to the d orbital, because I did say there's a d, but remember we said earlier that let's go back a page, the 4s orbital actually has lower energy, so that gets filled first. So we'd say 4s orbital holds the last 2 electrons, right? And that's the electron, that's 2, 4, add 6, 10, 12, 18, 20. That's all 20 electrons for calcium filled. After calcium, we move on to the 3d orbital. So let's do vanadium, which has 23 electrons again. So the s orbital are filled first. Then we use the second energy level, same sort of thing. P orbital can hold 6 electrons. Then the third energy level can hold 2 electrons. For the s orbital, the p orbitals can hold 6. And then the d orbital, remember the 4s can hold 2, but then you can put the d orbital here. The 3d orbital can hold 3 electrons. Okay, so that's when you can start moving. So make sure 4s is filled first, and you can put it before 3d if there's more clarity in your mind. That's the important, crucial thing where lots of marks are lost. So make sure you fill in the 4s orbital before the 3d. Krypton has 36 electrons. So you guys want to try that? Well, again, it fills in the s orbitals and the first energy levels, and the second energy level and sub levels also all filled up. At this stage, remember 4s is filled before 3d, 2 electrons there, and 3d can hold up to 10 electrons, and then only then can we move on to the 4p orbital, which holds 6, and that's 36 electrons. And we can do even more for a shorthand way of writing these electron configurations, because as you can see, especially once you get to krypton, it just becomes so tedious. But the way to sort of do an even more for shorthand, so for instance, if we wanted to do calcium, well, we could just take the noble gas argon, and we know its configuration, so it's 18 electrons, so that's 1s2, 2s2, 2p6, 3s2, and then 3p6. And we know calcium, so argon has 18 electrons, and we know calcium has 2 more, so it has 20 electrons. So what we can do is we can just write argon, AR, in these square brackets, just to denote that we've sort of accounted for these 18 electrons. And then we can just fill in the 4s orbital, just to say that, well, it's got 2 more electrons. And that's a perfectly valid way to write in the calcium electron configuration. So yeah, you can do that with pretty much any of the noble gases, but it has to be a noble gas that you write before. And the same thing really goes for ions. So sodium ion, so Na+, as we know, has lost an electron from its outer shell. So remember, the sodium atom has an electron structure of 1s2, 2s2, 2p6, and 3s1. Well, it's just lost this last electron in the highest energy. So the electron arrangement for the sodium ion is 1s2, 2s2, and just 2p6. Okay, so I think it can be tricky to conceptualize, but I hope this was a brief intro to electron arrangement and atomic orbitals. Yeah, if you want any more resources, please feel free to visit our website. We've got plenty more chemistry videos, along with other science videos and maths videos. So that's www.jctuition.net. Thank you for watching.